memory is filled, so it just cut off the abruptly. Sorry, yeah. Okay, so last time I tried the exercise, but it turns out that I can't solve it. So yeah, so yeah, I try to okay, yeah, okay. So let me just continue the proof. Okay, so okay, I think yeah, I try to see if I can post some solution to this homework. Okay, to this exercise. Okay, thank you. So anyway, so let me okay, so I think since I finished the part A, so let me see if I can prove this. Okay, maybe okay, so I think I finished the proof of part A, okay. And then I'm trying to wait. I'm trying to show the corollary 10.2.6, okay, which I already stated. Okay, so so very sorry. Didn't really support. So all right, so let me state the field. Okay, yeah, so I'll say the field for the corollary 2.2.6. So and given from x to x and this given check from x check to x be connected covering spaces of a connected locally has connected topological space X. Okay. That x0 be x, and then that is x hat 0 to be x0 hat, sorry, or x hat 0 doesn't matter, given inverse x0. Okay, and then that is x0 check for x. We use the gamma check inverse of x0. Okay. So if the gamma push forward of this pi 1 of x hat of x naught hat is contained in this gamma check push forward of pi 1 x check x naught check, then there exists a unique commutative diagram of corollary maps. Okay, so so the corollary map is so here is x check, and then you have this gamma check, and then you have this gamma hat, and then this is x hat, then this is x. Okay, this is gamma with with gamma hat of x naught hat is equal to x naught check. So moreover, if gamma push forward of pi 1 of x hat of x naught hat is equal to this gamma check push forward of pi 1 of x hat of x naught x check such as this x naught check, then this gamma hat is a homomorphism, and then if this x hat and x check are smooth manifolds, and gamma check are smooth covering maps, then this gamma check is a smooth covering map, and hence this gamma hat is a diffeomorphism if the gamma push forward of pi 1 x hat certain x naught hat is equal to gamma check push forward of pi 1 of x check certain x naught check. Okay, so I won't prove the. I think I'll just prove this one. I won't prove the. Yeah, I won't prove the smooth manifold case. Okay. So okay. So let's start the proof. So for the proof, okay. So the lifting theorem so remember this lifting theorem is the one we proved before, right? So remember, like we proved the lifting theorem, it contains actually 4 parts. One part is about the path lifting property. It's about like for each, basically it's like for each path in this X. Of course, this gamma is like a connected current space of a connected molecule space. And then you pick a base point at X. And then you are saying that you have a gamma that's a path in X with the starting point being X naught, and then, you let X naught be a base point of this X. And then there is a unique lifting of this gamma to a path in the X hat, which is the covering space, with the initial point being the X naught hat, where X naught hat you just choose it to be a pre-image of gamma inverse of X naught. Yeah, and also we have the path homotopy lifting property, where it is where you have a homotopy, then you can lift the homotopy with the same specified with the same specified starting point. Yeah, and then you have that the induced homomorphism, the pi push forward pi 1, and then you have the general lifting property, saying that if you have like okay. Yeah, so the general lifting property says you can have the phi from y to x. So here, instead of, I think the thing is, okay, instead of having a path, we are having like a actual you have a continuous mapping of a space y to x, and then so basically you have a continuous mapping of a a connected, locally path connected Brownian space y to x, and then with this y naught being the pre-image of x naught under this mapping. And then you also have a condition where the phi push forward of pi 1 y naught is equal to, is contained in this gamma push forward of this pi naught x hat x naught. Then there's a unique lifting of this phi hat from to the there is a unique lifting of phi hat of this phi, okay, with the same x naught. Yeah, with the x naught being the specified with phi hat of y naught equal to x naught check, okay. Where is x naught check is being defined, x naught hat is being defined to be the gamma inverse of x naught. Okay, so yeah, so and then you also have that if for every point y in y and every path gamma from a to b to y, from y naught to y, you have this phi hat of y is equal to lambda hat b, where lambda hat from ab to x hat is a unique lifting of the path lambda, which being defined as phi of gamma, with lambda hat a is equal to x naught hat. Okay. Conversely, if such a lifting phi hat exists, then you have this phi push forward of pi 1 y naught is contained in this gamma push forward of pi 1 x hat and x naught hat. Okay. So this is the general lifting property. Okay. So this is like the 4 theorems of the general lifting property. Okay. Oh, sorry. This is the 4th theorem about the lifting theorem. The 4th part of the lifting theorem. Okay. So the lifting theorem, and then so for the lemma 10.2.4 is the one that I proved, I showed last time, okay, which I didn't actually finish, but didn't, okay. Sorry for that, okay, all right. So, for the lifting theorem and lemma 10.2.4 gives existence and uniqueness of the commutative diagram. Okay, so okay, so so basically the idea is that here you have this x hat, and then you have this covering of x hat to this space x. Okay, so this is the covering space, and then you have this also you have this x check, right? Then to this gamma check. Okay, so and then you have this x naught is in x. And also this x hat naught is in gamma inverse of x naught. Okay. And then you have this x naught check is the gamma check inverse of x naught. Okay. Okay, so if okay. Okay. Lifting. Okay, I think the unique lifting is let me check. Uh, yeah. Uh, yeah. So okay. So okay. So I want to apply the general lifting property in this lifting theorem. So let me see. The continuous mapping of a connected with fast connected. Topological space y to x. It's very true that this lifting is that okay, this one is locally fast connected. Okay, so let's see if we can show that this x check is locally path connected. Um, let's see whether it's true or not. So okay. So what do you want? So okay. So let's see whether this is why this is true. So you have this because x is locally path connected, right? So any x naught, I want to show that there's a neighborhood that is path connected. Okay. So what is that neighborhood? So because this is evenly covered, so there's a pre-image local homomorphism. So therefore, local homomorphism means what? Is that there's a homomorphism onto it, right? Think because here you take the homomorphism and then maps onto x, right? And then for this neighborhood in x, basically what you have is that because x is locally path connected, so therefore there's an image of the projection of this point is lies in the that lies in the image, and then basically you know that there's a neighborhood that is in x that is path connected. So I want to show that because you take the intersection, it's an open set, and then you map it back. Okay. So I want to show that this you map the pre-image to like here, and then I want to show that this pre-image is path connected. So why is path connected? Because basically if I take any two point in this reverse neighborhood, right? So you take the projection because the local homomorphism, so it maps like any 2 points here, and then there's a path that's in this x locally path connected. So where you have this AB mapped to this path here, and then you compose this AB path to because the path has to be continuous, right? Okay, so I think this x hat is a locally path connected. Okay, so maybe I'll leave it as an exercise to show that. Okay. So this is given that okay, so since this x check is locally path connected, then what we do is that we can apply the okay, so since this yeah, so since this yeah, I want to say that we can apply it. Yeah, so since this yeah, this gamma check is continuous, right? And then okay, it's connected. Yeah, locally path connected. Okay. The virtual space y to x, and then yeah, this is it's a y to x. This is like x check, and then this y naught is belongs to phi inverse x naught. So yeah, this x naught check is belong to gamma check inverse of x naught, and then pi push forward. Yeah, we have the gamma check push forward is contained. Wait, no. I think there's an issue. Oh, wait. I think same argument shows also this. Wait, no. Is there like then there's a unique listing from y to x hat. Okay, so this phi push forward of y1 xy naught must be contained in this gamma push forward. So write it wrong, you know? Okay. Okay. Yeah. Okay, I screwed up. So let's draw this diagram this way. Okay. Okay. I think I just sometimes draw the wrong diagram. Okay. So this is x-hat, okay. And then, yeah, sorry, sometimes you may see the video just end abruptly because I set a, I set a time, I have to leave, because, I set a time alarm and then with alarm raised, then the video just cut it abruptly. So sorry if the video ends very abruptly or something. Okay. All right, here we go. So, okay, so we know that, Okay, so I think the same argument shows maybe this one, okay? Okay, yeah. Okay, so, so then we have our projection or our lifting, okay? The lifting is guaranteed, it's given by the, okay, so you have, okay. What about this x? Okay. And then, okay, give up for sure, okay. Oh. Okay, yeah. So we get a lifting, we get a unique lifting by the, with the, wait, what? Okay. Yeah, we get a unique lifting by the general lifting property. Okay. Yeah, we get a unique lifting. Okay. All right. Yeah. So, yeah. Okay. So then we have this unique lifting. Let's call this gamma hat. Okay. And then, okay, such that the, wait. Okay. Okay. Yeah. Okay. With gamma hat of x hat is equal to x check. Okay. I think that's given, that's given by the lifting property, okay. Also true, okay. So let's see moreover, okay. Let's see what happens next.